Okay, so welcome to the week 7 live session of this series, uh, the NPTEL course NOC24 EE-143, the Semiconductor Devices and Circuits tutorial. The course instructor is Professor Sanjeev Sambandhan from ISC Bangalore, and the schedule for my sessions is every Sunday 5 p.m. to 7 p.m. These are the details by which you can reach out to me if needed. Now the guidelines. As usual, in case anyone among you has any query, he can either unmute him or herself or just directly ask in the chat window. And please make sure that the microphones are muted, especially when you don't intend to speak. And let's try to make this session an interactive one. So for that, I would appreciate your cooperation. You may keep pen and paper handy along with the calculator. So that we could solve the problems together. The session recording link and the lecture notes will be shared by the NPTEL course team in the due course of time. The prerequisites include the last week's lectures, which covered the following topics, right? The bipolar junction transistors, they were introduced, and their IV characteristics, the non-idealities, and the equivalent circuit modeling was discussed, right? And before watching this session, either, in the live form or the recorded form, I'm assuming that you all have already attempted the assignment 7. So yeah, these were the topics that were discussed in the last week's lectures. Is there any doubt that anyone has regarding the lectures? Okay, so I'll assume no one has any doubt. So with that, we can move on to the first problem of today's session. Just a second. Okay, so the question is that a BJT has a current gain of 0.98 in the common base mode, right? Its current gain in common collector mode that is what we need to compute, right? So I guess I should wait for a couple of minutes. Please attempt this one. I'll wait for a couple of minutes. Okay, I guess I gave sufficient amount of time. Now let me discuss this question. Firstly, I'm assuming you guys know, right? What is common base configuration and common collector configuration? In common base configuration, the base terminal is connected to ground, right? And it is shared by both the input and output circuits. While in this common collector mode, uh, we apply the input signal at the base terminal and the output is taken from the emitter terminal, right? And the collector terminal in this common collector mode is common to both the input and output circuits, right? That everyone knows. Now we know, we'll write that it's given that alpha is 0.98. What is alpha? Alpha is the current gain. in the common base mode, which is equal to 0.98 as shown in the question. Now, this is your current gain in common base mode. Now, but we are interested in the current gain in collector mode, right? See, what is alpha by definition? Alpha by definition is your delta IE by delta IB, right? This is the current gain in, sorry, in, common base mode, this would be ICIE, right? Because the output terminal is collector and the input terminal is emitter and the base is common. So this is the current gain in common base mode. And what about the collector, common collector mode? In common collector mode, we define current gain by, we denote that by gamma, and that gamma is equal to delta I E by delta I B, right? This is your, I mean, current gain. In fact, I should write it. This is your current gain in, common base mode, right? And likewise, this is your current gain in common collector mode, right? Now, we know that, see, let me first tell you the approach. See, this, we know alpha, right? But we need to compute this gamma. So the motivation of the approach that would be employed to solve this problem would be to express gamma in terms of alpha, right? If we are able to do that, then our problem is solved, right? Because alpha is given. So we proceed as follows. Some of you would already be knowing this, I guess, or it might be already shown in the lectures, but still I'll repeat this part. Your IE emitter current is collector current plus base current, right? And so we have delta IE equal to delta IC plus delta IB. This means your delta IB would be equal to delta IE minus delta IC, right? And uh, what about this now? Gamma. Gamma is delta IE by delta IB. I'll replace this by this. Can do that, right? So I can write this gives me gamma delta IE whole divided by delta IE minus delta IC, right? Now, if divide numerator and denominator by delta IE, I would get following. It would be 1 by, this would be again 1 minus delta IC by delta IE. What did I do? I divided both numerator and denominator by delta IE, right? Now this delta IC by delta IE is alpha by definition, right? Which is the current gain in the common base mode. So we'll write, what should I write? Yeah, this gamma would be 1 by 1 minus alpha, right? This quantity here is alpha. So this would be 1 by 1 minus 0.98, which is equal to 50, right? So your gamma is equal to 50 in this case. That's how we solve such questions. Now, is this clear? Okay, I'll assume no one has doubt in this one. So the second one. In this one, the BJT has alpha equal to 0.98, the base current of 20 microamps, and ICBO of 200 nanoamps. You need to compute the exact value of the collector current when the leakage current is also considered. Fine. Compute the exact value of the collector current. Please attempt this one as it is a simple one. I'll wait for, I guess, 2 to 3 minutes. Please answer in the chat meanwhile. Okay, I guess I gave sufficient amount of time, uh, but I did not receive any, I guess, response in the chat. So yeah, I guess I'll do it myself now. So let me first write what was given. We were given the current gain, right? Alpha 0.98. We were also provided IB, which was 20 microamps, and ICBO, which was 200 nanoamps, right? Now, we know beta, right? What is beta equal to? Beta is alpha by 1 minus alpha, right? And if you compute beta, this would be 0.98 whole divided by 0.02, which would be equal to 49. Okay. And then once we know this beta, we can compute the exact value of IC, which is equal to beta times IB plus beta plus 1 times your ICBO, right? Which is equal to your 49 times 20 microamps plus 50 times 200 200 nanoamps, right? In terms of microamps, this would be 980 microamps plus your 10 microamps, right? Which is your 990 microamps, right? But we have been told to convert this into milliamps, so we'll do that. So this is your answer. IC would be equal to 0.99 milliamps. Fine. This is your IC. Now what about the next problem? Give it a try. So in this exact question, what would be the exact value of emitter current if we consider the leakage current? Okay. If we consider the leakage current, what would be the value of the emitter current? This is a simple one. I mean, Prasadra, would you like to attempt it? I mean, all you need is a basic trivial equation of BJT. What is the relation between the emitter, collector, and base currents? Hmm? What is the relation between IC, IB, and IE? Okay, so we know your IE would be equal to IC plus IB, right? This is something that you are supposed to know. Now we know IC, we know IB, we can compute IE. Your IE would be equal to IC is 0.99 milliamp, B is 0.02, right? So your this IE would be equal to 1.01 milliamps. Is this clear? Right? Fine. The next one. What's the error percentage delta IE by IE in calculating the emitter current when the leakage currents are neglected? in common base, common emitter, and common collector configurations. So how will we attempt this? I mean, you have already computed IC in which leakage current was considered, right? Now the question is saying, don't consider the leakage current. Compute IC without leakage current, and then compute the percentage error in delta in IE, right? Delta IE by IE. So in my opinion, this is a simple one. So I expect you to answer this. Wait, I'll copy the relevant equations and then wait for you. Right, this is your collector current with leakage. Right. Uh, and specifically this is the component that contributes to the leakage one. So this is without leakage component, right? Now you also know this one, right? You know that your IB is 20 milliamps. And you also know this equation, right? So now you are interested in finding delta IE by IE, the percentage, right? You need to compute this one. This would be your IE with leakage minus IE without leakage, right? And we'll divide that by, uh, let's take with leakage one, right? IE. I mean, this is the fraction of interest, right? And then you will convert that fraction into the percentage, right? Compute this one. You have all the relevant info, right? This is that leakage component. This is the without leakage component. Use this equation to compute IE. IB is given. Compute this one. I'll be waiting for 3 minutes, okay? I'll give you 3 minutes. So uh, you have time till, okay, we'll resume at 5:28, okay? Attempt this question till 5:28. I'll be waiting. And once you find the answer, just type in the chat which of the options is correct. Okay, I guess. Okay, we have one. Good evening. Which topics? I mean, what does that even mean? I mean, which topics have more chances to come in the exams? I mean, all the topics are important, right? All the topics have their due weightage. And again, I mean, I'm not the instructor, right? I'm just a TA. Such questions you may ask instructor. I'm not the best person to answer them. I thought somebody had solved it. That's why. Did you guys try it? 1.9. No, that is not the correct answer. I mean 1.9%, right? No, that is not the right one. The other student, Prasad Rao. Did you attempt it? Yeah, I'll take that as a no. See, IE with leakage would be IC plus IB, right? In fact, wait. We have already computed this, right? IE with leakage is this one. I'll directly use that. 1.01 mines. What is IE without leakage? This would be beta times IB. What is beta times IB? That is 0.99. Just a second. We can in fact simplify the matters for us. Let's write this IC plus IB, right? Because IC is the with leakage, this one, right? And let's consider IC dash as beta times IB, which would be the without leakage collector current, right? So this would be plus, sorry, minus your IC dash plus IB, right? Whole divided by IC plus IB, right? This is your delta IE by I. And this would be, what is IC plus IB? Your IC plus IB would be, now this IB and IB goes, right? We are left with IC minus IC. IC was equal to this one, right? 0.99. And what about this IC dash? Your IC dash would be simply beta times IB. And what is beta times IB? Your beta times IB would be 0.98, right? This part is your this part. So this is 0.98 whole divided by your 1.01. Why? Because IC plus IB is IE and that was this, right? Because this in the denominator I considered the leakage one, right? So where we have to neglect leakage. Did you got the question first? The question was asking that you need to compute the percentage error, right? Delta IE by IE in the calculation of the emitter current when the leakage currents are neglected. So compare the cases. We'll compare the cases. We'll compare the cases with and without leakage, right? Okay, fine. 0.99 minus 0.98 whole divided by 1.01. Fine. Right. Therefore, this delta IE by IE would be equal to 0.01 whole divided by 1.01 into 100. That would be equal to 0.99%. Fine. So, which option is correct? Option A, right? Option A would be the correct one. Now, the question fifth. Mm, you may attempt this one. Fine. The intrinsic gain is an important parameter of a BJT when used as an amplifier. You may consider two transistors, T1 and T2, that were biased to have same transconductance. T1 has an early voltage of VA equal to minus 100 volts, and T2 has an early voltage of VA equal to minus 10 volts. You need to select the option that best, select the option that best compares the intrinsic gains of the two transistors. Okay, that is what you need to see. So the hint is that the intrinsic gain is the product of the transconductance and the output impedance of a device. Please attempt this one. Okay, I guess I'll show this question now myself. This is the fifth one, right? See, uh, from the info that was provided, your ID, VDS, VA, right? And this is early voltage of minus 100 volts for this, what should I say, transistor 1, right? T1. Now what about this T2, right? Uh, ID, right? This is a eraser, just a yeah. Let me first point this early voltage and then we will right. This is your minus 10. This was your, what should I say, VA, and this is your VDS. This is your T2, right? Now, your gamma 01 would be equal to your VA1 all divided by ID, right? I mean this modulus of this. And similarly, your current gain for the second one would be your VA2 all divided by your ID, right? Clearly, gamma 01 is greater than gamma 02, right? Which implies that your GMR1 is greater than GMR02. Yeah. So your T1 gain is greater than T2 gain, right? Done. This is your Q5. Right? So that is why this T1 would be greater than T2. Is it fine? Okay. Now we'll move on to the sixth question, in which we need to select all the correct options, which can result in increase of this transistor beta, right? Uh, uh, the options are, does beta increase as base width increases? Does beta increase as minority carrier lifetime in the base region increases? Third option is, does beta increase as the temperature increases? And the fourth one is, does beta increase as the temperature decreases? Right? These are the four options. Now listen. Option B. See, beta does not increase as base width increases. About the second one, right? For the second one, does beta increase as the minority carrier lifetime in the base region increases? Well, it does. Reason being, uh, your beta increases with increase in minority carrier lifetime. As the rate of recombination reduces, right? And more of the injected carriers are able to cross the junction, right? right here. Beta would be equal to IC by IB. Is it fine? So this one is a correct one, right? So we'll take this one. Likewise, we have with increase in temperature, the lifetime of minority carriers increases, right? In the base region, which increases the beta. But due to the rise in temperature, the transit time tau increases, which reduces the beta. So net effect is that beta increases the temperature, right? So let's continue the sentence. So, but rise in temperature the transit time, your tau, right, increases, which reduces your beta. But the net effect is that your beta increases with temperature. Fine. So we'll take this one as well. Yeah, two options are correct. I mean, you were asked, right? Select all the correct options. So it was, I mean, you can say multiple selective type question. There was not only, I mean, single correct answer. There could have been more than one options that were correct. That's why two options were correct. Is it fine? Okay. So now we move on to the seventh one. I mean, we need to consider two BJTs, T1 and T2. The specifications are as follows. For the T1 emitter, doping is 10 to the power 20 per centimeter cube. The base doping is 10 to the power 16 per centimeter cube. Collector doping is 10 to the power 19 per centimeter cube. And the following are the specifications of the T2, right? The emitter doping is 10 to the power 20 per centimeter cube. The base doping is 10 to the power 16 per centimeter cube. The 20% of the collector region doping, I mean the 10 to the power 14 per centimeter cube, and 80% collector region doping is 10 to the power 19% per cube. You need to help a student choose the above transistors for the following applications appropriately. Application 1 is for amplification of an EEG signal. Okay. And the application 2 is for the voltage regulation of a 60 volt solar panel. So these are the two applications. So now, which transistor should be used for which application? That is precisely what the question is asking. So what should we, how should we answer? Yes, I'll do that now. See, in power MOSFETs, we introduce a drift layer, right? I'm assuming you know that part. Let me still write that. In power MOSFETs, a drift layer in mines is introduced, right? Right. It is responsible for it is responsible for supporting high voltage and enhancing MOSFET's performance, right? In, of course, the high power applications. It is made of a lightly doped semiconductor material, right? So in the above example, T2 has a drift layer, right? This is a drift layer, right? I'll write this one as well. So clearly T2 has a drift layer, which makes it suitable for power applications. Right. So the application 2 is the power application, right? So I'll write this as application 2. Now, your T1 is a signal level MOSFET, right? Which is suitable for application 1 because amplification of a EEG signal is such application. So which option is correct? So T1 was for application 1 and T2 was for application 2, right? So this option is correct, right? What about the eighth one? The last one is a theoretical question, right? So which of the following statements are true? Again, a question in which multiple options can be correct, right? So which of the following statements are true with respect to consequences of early effect in a BJT? One or more than one correct answers can be there. So is A the correct answer? Does base width reduce? I mean, as the base width reduces, does the chances of the recombination within the base region decreases? Is that the case? That is not right. So, I mean, the first one is not true, right? So alpha does not increase with increase in this VCB. What about this second one? The concentration gradient of minority carriers within the base decreases. Is this a correct option? Does the concentration gradient of this, minority carriers within the base decrease? It does, right? This would be right one. What about the third one? When reverse collector base voltage is very large, effective base width WB may be reduced to zero. Yes, it may cause voltage breakdown, which is known as a punch through. This is something that you know, right? And emitter current increases with increase in the reverse collector base voltage. True, right? This one is also correct. So turns out three options are correct for this question. Only the first one is not correct. So with that, I'm done with the questions that I planned to discuss. Does anyone among you have any doubt regarding today's session? Specifically today's week live session. I'm getting difficulties in the previous 2 weeks. Topics are difficult to understand. For that you need to practice more, right? I mean, go through the lectures again, watch these live sessions again, and practice problems apart from this live session problems. I mean, that is the only solution I have, unless you have some specific doubt. It happens with everyone. All I would say is you need to put more effort. Yeah. Any other query? I didn't get reply from the course instructor for previous year papers. Then probably previous year papers, I mean, you won't be getting access to that. Otherwise, the course instructor would have replied, right? And it's same for everyone. You are not the only one who won't be having access. If it's same for everyone, then it's even game, right? Nothing to complain about, right? No one will have access to previous year papers. Fair game. Fine. And uh, how many assignments are done? I mean, for which the deadline is over. This was seventh one, right? For this one, the deadline won't be done. But what about the sixth one? Okay, sixth assignment deadline is over, right? Okay, so six assignments have been done. Fine, halfway through the course, right? 12 weeks, six are done, six more left. Anything else? Uh, Prasad Rao, any doubt? Since you guys are only two students who are attending this session, I mean, I can only ask from you two. The rest will probably watch this in the recorded form, so I cannot ask them the doubts. I mean, if they do have a doubt. Fine. So should we end the session then? Unless you two have something in particular. Fine. So yeah, we'll end the session right here. Thank you for tuning in. Bye. Thank you. You may leave the meeting.